I'm a blue box. I can't teach like a blue box. And then we can look at number 24 and 6-4.
Just the part about finding the Y-intercept. I know you substitute 0 for X, and then you solve for Y essentially, but I'm getting stuck where I don't know what to do basically. So I have it figured out to log 2 of 2 minus 5 equals Y.
Yeah, what's log 2 of 2? So remember, you've got it. Go ahead.
Oh, no, go ahead. I'm confused.
You've got to internalize the question that will represent. We have unconsciously, seemingly, internalized the meaning of a square root symbol. We got to do the same thing more consciously now with the logarithm symbol. So what is a logarithm asking for? What is it always equal to?
Okay, so would it be for the log 2 of 2, would that be 1?
Yes, because that's the power that 2 needs on to come to. Yeah.
Okay.
The logarithm is always asking, what power does this thing in my base need to become this thing inside me, which is really one of the craziest way to phrase that, but that is basically what it is. Yes.
Okay, got it. Thank you.
What power does the base on me need to become the input of me? That might be a little less creepy way to say it. Anything else, guys? Oh, I have a question on 6-5. Okay. I'm ready. Number 27. Okay, let's see. 6-5. 27. There you go. Oh yeah, I love this problem. I would. All right, let me stop sharing and bring it over here. Oh yeah. All right, let me see. This one is definitely a strange one, and when you first look through it. What was it again? 27. Okay. Oh shit. Okay, just a minute. I got another question. All right. So this one. So of course I'm going to do this. But they tell you. So look at what they tell you. You know that this is true. And you know that this is true. Oh, did they screw up? Is that what they did? No, they didn't. No, maybe. No. This is interesting. Maybe they didn't. No, they did not. Okay, this is interesting. This is a little more interesting than I thought it would be, which is really cool. 28 is kind of freaky. But let me see. What's one way I could break this up? Who's talking to me? Let me see. This is so exciting. Okay. Okay. Whatever floats your boat. Let me just kind of give us the first step on this one, since this is an example. What if I rewrote this as 11 times 5? Is that helpful at all? This is interesting. I like this. This is not exactly what I was expecting. So, I mean, for example, let me think if there's another way to do this. I thought I could see. I mean, this one actually, real quick. This one's weird. I don't know if they meant it to be like this, and I just got to think about it now. Do you guys, what do I use to rewrite? Let's look at this one real quick, because I think this one's going to work a little more directly, and then I got to think about 28. And then the actual problem you have to do is 27, which is actually easier than these two. How can I rewrite this because of what it is inside? How can I rewrite that using properties of logarithms? Somebody can do that for me, right? Are you guys out there? Hello. What's the rule when I have log of a division? Log of a quotient.
Subtraction. So log 11 of 6 minus log 11 of 11.
Holy shit, Jeff. Come on, you can do it. There you go. Log base 11 of 11. Log. This piece is easy. What's that piece?
1.
1. I like it. This piece is interesting. It does say, oh, I see. Okay. Oh, well, they give you a huge hint over here. I like it. Okay. All right, now I see their freakiness. This is a huge hint as to how to do these problems. So I was trying to pigeonhole them into a certain type of problem, and that's not even the type of problem they're going for. The type of problem I'm thinking about dealt with properties of logarithms and rewriting it in terms of these known things. You have to use this on these problems. So for example, let me take a step back. So if the point of these problems is to use the change of base formula, which I don't know if you guys remember, but should I use B for the base? Sure, I don't care. This will be log base anything of M over log base anything of B. That's the change of base formula. Remember the base is on the bottom? Remember that part? And normally we would use log or ln because those are the things that are in our calculator, but the rule doesn't give a shit which log we use. It's true for every log. Any base I want to use, I can break up any log like this in terms of that base. So obviously, considering what they give me, what is the base I want to go to?
5.
Yes, I want to go to 5. So let me erase my pathetic earlier attempts at this. Get out of here. All right. So if I rewrite this in terms of base 5, so log base 5 of something over log base 5 of something, what's going to be on the bottom? Log base 5 of
11.
I'm sorry, I'm looking at this
sorry,
one.
6. Sorry.
Yeah, so the base is on the bottom and the inside's up top. Now the bottom is exactly equal to what? What's the bottom? What's log base 5 of 6? Don't give me a number. What do they tell me?
A.
And the top, I can do what I was, now this is the kind of problem I thought it would be. You can break this up as 5 times 11, right? Okay, and then you would keep going. This is what? It's 5 times 11, so how can I rewrite this one logarithm? I can write it as 2 logarithms doing what?
Adding.
Adding, I love it. And of course, log base 5 of 5 is 1, and log base 5 of 11 is B. Kabam. So if you change the base to the known base, that's the first step you want to use, is rewrite it using this property. I like it. I like that problem. That was nifty. See, that's how I get myself in trouble, is I assume what they intend a problem to be without just actually reading more, which is something you guys learned from my mistakes. Read the full instructions. All right. Is that okay to get you going with number 27? Whoever was asking that. Okay, I don't know. Is that all right? Person? Yes, okay, thank you. And of course, it's fine if it's not okay, you can just tell me. So another question is number 42. It's not so much a question as it is an answer. Let's see, 42. Oh, dude, yeah, this is yummy. So extensions, that's some bonus stuff going on. So this one is just, you got to play around with this shit. So if this is true, that means that the power 81 needs to become 2401 is somehow equal to the power that 3 needs to become 7. And I'll tell you one clue. 81 and 3, oh, look at this, neat. How did I do that shit? 81 and 3 are connected very directly. So you should be able to use that fact to help you rewrite this stuff and just play around with it. So let me tell you something interesting about Math 176. And you're going to see this fact very soon, if you haven't already. This is the math where a big part of it is being comfortable playing around with math. I don't think you get as much of a chance to do that, or even it's just an expectation of how to really learn pre-calculus. There's an expectation of playing around with shit. Not with shit, but with math. And you don't get that experience where it's so regimented up through 110, up through intermediate algebra. And this is the first course where you really, very many of the problems we're going to do is going to involve trying something out and then realizing it won't work. So you go back and you try something else out. Just play around with some stuff. That's part of the whole process. So number 42 is a perfectly beautiful, you just do whatever you can with that shit. You bring in some variables, you rewrite 81 in terms of 3, you rewrite logarithms in other forms. Yeah, all right, that's all I'll say about it. How's that, everybody? You guys all right? Anything else? Did I miss anybody? I don't think so. Okay, all right. I don't see any more questions, so we're going to get back into where we left off. How many people do I have? Man, I don't know. Did that email I sent out have the opposite effect of what I was hoping? Oh, got to look and see how many people are still in this class. Won't take it personally. All right, so I want to pick back up where we left off.
You can see a lot when they run around.
What's that?
You can hear, you can see the particles on the ground from running, and you can also see the potion.
You can see the particles on the ground and the potion. All right, this is too deep for me. I don't know what to do with that. All right, I'm going to mute everybody. All right. I don't know. If you got to do that stuff, you got to bring enough for the whole class. Now, somehow distribute it. So, all right, just to kind of catch us up with what we did last time. Oh, let me do this for myself before I go crazy. There we go. Okay. So we started off kind of slow. We defined what an angle was. It's an intersection of two rays, right? So we have a ray and a ray. Vertex, not so interesting. We talked about the variables that we're going to see. We could see anything from some Greek letters. We can use just our capital letters. We like using capital letters for angles. And who knows, maybe some other things. Let's see what else was important. We talked about standard position. There we go. Which really just means lining up the initial side of an angle with the x-axis. So this will be 0 degrees or 0 radians. So then if I have 45 degrees, let's see if anybody remembers what radians that is. So let me bring back in radians. We all know degrees. We know degrees pretty well. What was the idea of a radian? What's a radian directly related to?
It's directly related to 180 degrees, right?
I like it. It's
The circumference of a circle.
the circumference. I like it. But why do we call it a radian? Radian, because it is the radius. If I took the radius all right, and I took it and I bent it and put it on the circle. Don't do the stomach joke. This angle it goes through is a radian. Now think about that. That's so beautiful. So instead of instead of using made up degrees, we just picked the number 360 because it's very divisible by a lot of things. So that's why we picked 360. There's nothing special about 360 in circles, not a damn thing. Right? We just happened to pick it. We could have picked 400 because 400 is divisible a lot of different ways too. But instead of using made up shit, we say, why don't we just use how far a radius would bend around a circle, and that angle would be 1 radian. So then the name kind of makes sense. It's a play on radius. And from that, let me just stop there. I want to really make sure you guys understand that, because I remember when I was taught this stuff, that was not made clear. And that didn't mean I didn't know how to do the math. It would have just been more interesting to me to realize that's what the hell a radian was. So I want to make a big deal out of that because it's really freaking cool. So from this, so how many radians is it to go all the way around the circle? I think that's what somebody else was saying. So how many radians if I want to go all the way around? Somebody chatting at me? No, I'm just saying.
Is it 6?
Oh, I see what you're doing. 6.28, sure, double pi is 2 pi, right? So to get all the way around the circle, it would be 2 pi radians. Like it, maybe. So something to realize is, let me see if I can make this picture good. So if I want to kind of reconstruct the lecture I did last time, the whole circumference is 2 pi r, right? So if I define, so here's what we're really doing when we define an angle in terms of radius. I want to kind of take away, let me see how I can say this. So this is 1 radian. Let me see. I don't want to say this. Yeah, so so here's what I did last time, which made it, I'm trying to stay away from redoing my whole lecture, but I might as well. So if I had a larger circle, this would still be the same angle for both circles, of course. Is that cool? This is what we did last time. Yeah, not yesterday. So this angle should not depend on what the actual radius is. It's kind of, in a sense, it's independent, because if I made it a larger radius circle, it would just curve around and come right back to the same place. Let me stop there for a minute. Does that make sense? The angle itself should not depend on how large the radius is.
That makes sense.
I like it. So what I do is I'll say, whatever the radius is and whatever this arc length, yeah. What will always be true is if I divide the arc length by the radius, I'll get the same number no matter how big the circle is. So if I take the arc length, why are you having trouble spelling? And I divide it by the radius. Right, so the actual variable we use for arc length is s. That is what we're going to call the angle in radians. So if you come back, when the arc length is, if the arc length was 1 radius, then r divided by r is 1 radian. Let me stop for a minute. Why are you, I gotta tighten this bad boy up. You keep wanting to just go to sleep. Come on, poor little dude. So, does that make sense by itself. That's the whole idea. If this is one radius and then this is one radius, they all reference the same angle. So that's why I want to take this divided by this. And that's what we're going to define as the angle in radians. So for the whole circle, what this arc length is going to be is, of course, 2 pi r. So if I use this idea and I go all the way around the circle, I've gone 2 pi r. So my angle will be 2 pi r divided by r, 2 pi. So all the way around the circle is 2 pi radians. All right. So again, this was supposed to be a shorter version of the lecture, but it's kind of hard to get to this point without doing all this. That leads us to an interesting connection between radians and degrees. And real quick, I just want to write this in a different format. If I solve this for S, this is a very important formula right there. Can somebody tell me, if you're paying attention, what must this angle be in? Can it be in radians or degrees, or does it have to be in a certain units? This angle that I use here.
It would have to be in radians, right?
Has to be in radians because this is the radian definition. So if I ask you in a future thing and I say find the arc length of a circle of radius 7 and the angle is 7 degrees, you can't plug a 7 here. It's got to be radians. Otherwise, it doesn't make any sense. So that is one of the main reasons we develop an angle based on actual physical measurements instead of a made up thing of degrees, is because then I can plug numbers directly into it and they actually represent physical quantities. So if you ever see an angle sitting outside of a function, outside of a trig function, it's pretty much got to be in radians because that's what makes it be a real physical quantity. Okay. So here's our first little official formula. It comes right off of how we define radians. And of course, the relationship we made between degrees and radians is we realized that 2 pi is all the way around, and that's equal to 360 degrees. So then pi is 180. So if I wanted to know 73 degrees is how many radians, what would I do?
$73 degrees times pi over 180 degrees.
Yeah, one thing you can always do is this. Make the little grid, put degrees down here so they cancel, and put pi up here so you get radians. So then it's whatever the hell 73 divided by 180 times pi is, whatever the hell that is. I actually don't care. But whatever the number is what the answer would be. So that's how I convert between degrees and radians and vice versa. All right, I like it. So we have a different method we want to use to identify the angle in a circle. I need to know, if I know one way, how do I convert it directly into the other one? So that's how I do it. That's like feet to inches. Okay, I like it. So I think the only new thing we've done so far is I didn't write this formula up here before. S equals R theta. I'm going to keep it over there for the moment. All right. I don't know if anybody did that. I think it's going to be 1.17. Is anybody doing that? 1.19. I don't know. Nobody's doing that? Nobody's going to help me out? Okay.
It's 1.2741 rounded.
Like, I'm okay with that. I'm okay with being that far off. So if I have an angle, let me see if you, so if I had an angle and wanted to, the angle, let's say angle A. So angle A, let's say is 27 degrees. You should be able to approximate what that looks like on the graph, right? So 27 degrees, this is 45, 27 is not quite half of that, so maybe right there. It doesn't have to be perfect. What do you think, is that cool for everybody? That's roughly 27 degrees, maybe? Maybe a little bit less, I don't know. What do you think about this? How would you graph this? Negative 10 degrees.
Would it be in the fourth quadrant of the graph?
I love it. So this is 0. So this way is positive, this way is negative. So this is kind of a really nifty circular number line in a way. If I go this way, it's positive. If I go this way, it's negative. Instead of this way is positive, this way is negative, it's just kind of rolled on itself. So that's nifty. So this would be maybe negative 10. So of course, you should immediately be saying, okay, man, we just talked about radians, but I wanted to get that idea. So what if I throw this at you? Where would this be? What would that be? So since radians are brand new to most of us, it might be a good idea to first change that to degrees. And there's a really quick way to change this to degrees because pi radians is the same as
180.
Yeah. So then what's this angle in degrees?
30.
30 degrees. So anytime you start learning a new language, you're going to have to kind of, you kind of translate back to your language as you're learning the language. That happens. So math is not different at all. Anybody out there who's learned a separate language, you know what I'm talking about. Eventually, we are going to just look at this and know that it's 30. And one nifty thing, so if I wanted to approximate this, it would be a little bit bigger than 27. So there would be my pi over 6. And watch this, it's kind of cool. What would this be? This would, of course, be
60.
60, because 180 divided by 3, which is a nice analogy. You know, I mean, it's beautiful. Some good symmetry there. So obviously, I'm kind of focusing on these because they're going to become very important. So for example, 60 is a huge angle measurement in geometry. 60, 60, 60 is equilateral, right? And then you can do some other shit, make some 30, 60, 90 kind of stuff. And of course, another one's going to be big is this guy. What's this guy?
$45.
Yeah, another way to look at him is this whole thing is 2 pi. Half of that is pi, right? Half of that is pi over 2, and then half of that is pi over 4. So that's going to be 45 degrees, right in the middle. And if you just plug a 180 in and divide, you'll get your 45 degrees. I love it. All right. Kick ass. Kick ass. One other thing that gets interesting, to let you guys copy that. What about, so what about this? Let me go one step further. What if I have this angle? Where would that be? And what's kind of special about that angle?
You just keep going, right? So if you go all the way around once, that's 360, and then you just keep going.
Yeah, so you can subtract. If I go around once, that's 360. So let me take 360 off, and then what's left? Thank you, everybody. All right, and then 152. So let's try to do some degrees here, because if you don't know the degrees, the radians are going to be that much harder. So that's 45. That's 90. What's this? 45, 90. What's this? 45.
90, 135. So then 152 would be in here somewhere, because this, of course, is 180. Is everybody with me? You guys are? What would this be? What angle is that? Represent?
270.
Yeah, 270. Just a big old step of 90 from there to there. We put some degrees on there, and of course, this one would be what? So 45, 45, 45, 45, 45 more.
25.
320. Right, and then you can keep going, and then another 45 will be 315, and then you get 360, which is equivalent to 0, and blah, blah, blah. So let's do the whole thing again with radians. Kind of want you to start messing with radians by itself. So if I do radians, this is 0. What would this be? What's 90? Let's do this. All the way around is 2 pi. Let's kind of work backwards. So this is obviously going to be, so all the way around is 2 pi. This is
Pi.
pi. And this has to be what? 0 to pi, so this has to be
1/2 pi.
half pi. I love it. Pi over 2. And this we just talked about a minute ago, right down the middle.
Pi over 4.
4, I love it. So that's 1 pi over 4, 2 pi over 4, which is pi over 2. Is that cool? And then this, of course, will have to be
3 pi over 4.
It's crazy. And then 4 pi over 4, which is pi, and then unbelievably,
5 pi over 4.
holy shit, and then 6 pi over 4, which is, what's 6 pi over 4? That reduces to?
3 pi over 2.
Which makes sense because it's right between pi and 2 pi, right? And then another, so that was 6 pi over 4, so that'll be 7 pi over 4, and then that'll be 8 pi over 4, which is freaking 2 pi. So you got to start getting used to thinking in terms of this. And in fact, we're going to fill in the 30 and 60 stuff also eventually. I just want to stop there for right now. This, of course, is definitely harder because degrees are normally in whole numbers, in decimals, and radians are very often in some fractional multiple of pi, right? So too bad, it's the way things are. So if I wanted to know where I had an angle 5 pi over 6, where is that going to be? What's a good way to look at that? It's almost what? 5 pi over 6. It's just a sliver of pi away from what?
From pi.
From a whole pie. Somebody came and took 1/6 of my pie, ate it, and left.
Rude.
So it's not here, it's a little bit,
Less.
I like left, that's neat. So you mean looking at it like that? Okay.
I said less.
So,
less.
oh, less, okay, I'm sorry. I think you said left, and I was like, that's neat. That actually sort of works. So yeah, 5 pi over 6 will be right there. And that might not, you might not have known where it was supposed to go, but I just remember over 6 is increments of 30 degrees. So this angle here, what is that angle in radians? You pretty much know what it is based on what we just spoke about. What is that angle by itself?
30.
Yeah, be less degree-ish, be more radian-ish.
Pi over 6.
Yeah, because it's 5 or 6 away from a full pi. Let me stop for a minute. This little dude is going to become very important. This is what's called a reference angle. These are going to rule a big chunk of our life very soon. The idea of a reference angle. So it's always in reference to the x-axis. The closest distance, the closest it can get to the x-axis. So something over here is going to be in relation to the positive part, and something over here is going to be in relation to the negative part. Does that make sense? So this guy's reference angle would be what? for him? How much past pi is he?
Pi over 4.
Yeah, 4 pi over 4 is a whole pi, and that's 5 pi over, so it's pi over 4 away. So the reference angle for this angle is pi over 4. Right now, it's just an interesting side note. Later, like I said, it's going to be crazy huge. Yes, somebody's asking something that's coming our way. Athena, I'm sorry, I just called you out. So I'm sorry. Can you explain your question a little more?
It was
Or is that-
something you were doing before, but it's okay. I understand it.
Okay, so okay. Sorry, I missed it. I'm not always looking at the chat when I'm up at the board, so I'll try to do a better job. All right. So this is kind of nifty. You have to trust me. I think that some of you guys might actually do this. If this is the first time you've ever seen radians, you just want to kind of construct this thing for yourself, and you want to figure out what like 3 pi over 4 is, and what 11 pi over 6 is, and where it would be. That would be remarkably useful for you to do. Sort of like making flashcards of vocabulary if you were taking Greek class or something. Or maybe, you know, maybe not Greek, I don't know. Maybe German. There you go. Okay. Let's see, what else did I want to talk about? That's about it. Yeah, that's about it for that. I like it. All right. We're going to take a little side quest for a minute because this is going to come back in a big way in a little bit. So radians are always behind the scenes. This formula and another one require radians. So let's do this first. Let's use this equation over there. What if I knew I have a circle, a radius, what, Jeff? 7 meters. And I know I walk the circumference. I walk around the circumference. How can I word this so my grammar actually is good? Through an angle of, sure, that's almost good, Jeff. Through an angle of, you could do it, buddy. You can still do it. There you go. 6 degrees. How far did I actually walk? So this is the connection. So remind me, obviously R is radius. Obviously theta is angle, but it has to be in what? Like we said earlier.
Radians.
Radians. So anytime you see theta out in the world by itself, it has to be in radians. Unless I'm in a really strange situation. So what the first thing I got to do then is attack this dude. All right, so what do I know? I know R is 7 meters. I know theta is 60 degrees, which who remembers what that is in radians?
Pi over 3.
Pi over 3. So now to figure out how far did I walk, what the hell does S mean again? What does S mean? Of course, it references something that has no S in it, which is hilarious. But what is S?
Side including how far it goes around the circle?
Yeah, it's something called, I think you got it, it's something called arc length. So in if you want to say it more in English, it's the distance I actually go through. I actually walk around the circle if I go through a certain angle, so which is exactly what this is asking. So this means arc length. So obviously they chose the letter S, right? What else would you choose for arc length? I don't know. So this is asking for arc length. I just got to throw everything I know. 7 times pi over 3. And then whatever that is. It's going to roughly be 7 point something because this is almost 1. 04, so 7.28.
Man,
7.33.
33. Okay, I can live with that. 7.33.
04 if you round it. Oh, okay. 0.382.858. Oh, meters. Sorry.
All right.
Looking for units.
Thanks for going with me on that, Jason. You're like, what the hell does this guy want from me? Yeah, so units are huge. Okay, let me stop for a minute. So this, the interesting thing about this is, I want you to realize something. If my angle was 2 pi, if theta is 2 pi radians, if I walk that many radians, didn't I walk around the whole circle? So shouldn't the distance I walk be equal to the circumference? And so if I put 2 pi in, don't I get 2 pi r, which is the circumference? I mean, and of course that's kind of silly. You're like, well, duh, Jeff, we built it off of that idea. So of course I get that back, but it's kind of nice to see an old result coming from this relatively new equation. Okay. I like it. So just really be careful. Remember, the angle must be in radians. And that's generally a good idea to start just getting used to radians and using it almost everywhere, unless the problem gives you something else. Okay. Keep that guy up there. Now watch this. This is going to be kind of nifty. What is the, so this is all about distance around the circle. So if I want to go a piece of the circle, I can then figure out exactly how long that is by using this formula. So that's all about length. So of course, if I want to go one dimension up, I'm going to talk about area. And the area of a circle, amazingly enough, is pi r squared. But so then in terms of angle, what would the area of, let me put this out here. What would this area be here? What would that area be? So this is a radius r. So the whole area is pi r squared. So it would have been easy if I would have just given you this. You could have, that would have been easy, right? If I said, what's this, right? And it's not like an emo circle that has his hair coming down. No. What is the area? It would just be freaking half of that. Why didn't you give us that, Jeff? What is this shit? Some undefined angle? But it's exactly the same idea. How do you know this is half? Well, because visually it's half. But how do I know it's really half? Because I've only gone halfway around. What is the angle of this? What is this angle that I've gone through?
180.
True, but not good enough.
Pi.
Okay, thank you. It's pretty cool, that. So, and the whole way around is 2 pi. So if we really think about this, why is this 1/2 the total area? Because the ratio of how far I've gone here to the total distance around is 1/2. Let me stop for a minute. So what would it be here then? So really what I've done here is how far I've gone divided by the total distance is the fractional part of the whole circle I've kind of covered times what the whole area is. So it's that fractional piece of the whole area. So what would I put in front for this guy? Well, the whole distance is 2 pi, and how far have I gone?
The undefined variable.
Yeah, theta. And notice what happens here. Something very interesting happens here. Or maybe not that interesting. What happens here directly?
Pi cancels.
Yeah, the pi's cancel. At least that happens. I don't know what the hell r is. I didn't tell you what theta was. Too damn bad. But at least the pi's go away. So a better way to write this is 1/2 theta r squared. That is the area of a sector, which I don't know if I've used that word. That's what we call a piece of pie is a sector. This is called a sector. I want to show you a really funky ass derivation of this formula, because and to be really honest, I think you normally see it as r squared theta, but I really want to show you this because it's so freaking cool. If I take this slice, let me take that slice and put it right here. You do what you want to, and this is theta. What is this length here? Let me call it, this is r, that's theta. What is this length here again? You could do it, you could do it. What is this length here? How do I get that?
Arc length?
Arc length, which is equal to what?
R
S-
times theta.
R times theta. So let me put that there. It's R times theta. Now watch, this is so cool. And there's actually, once you learn a little bit of calculus, you can actually kind of prove what I'm about to say more specifically. But I just like this. We already showed it officially here, but let me just show you a different way to look at it. Pretend like this is straight. Pretend like this is straight. What would the area of this triangle be? Well, how tall is it? R. Isn't the whole thing R throughout? So the height is R, and the area of a triangle is 1/2 base times height. So wouldn't this be 1/2? The height is R, and what's the base?
R theta.
R theta. Isn't that 1/2 R squared theta? Isn't that exactly? Isn't that cool? Or no? You guys are like, dude, we're so past me being able to tell if something's cool right now. I understand. So I am hoping that some of this derivation got through. So we have this bad boy here, which is really the definition of radian just repurposed, just solved for x. Then we got this bad boy here. If I can figure out a part of the circumference, I should be able to figure out a part of the area. Okay, maybe. All right, so this is less official, but interesting. And this is official. So what I want to talk about now is, unfortunately, I have found flat Earth video people on the YouTubes, and I watch a couple of those and I go a little insane. So they do not understand what we're about to talk about, which is angular velocity. Right? So if I have a record, say, do you guys remember records? There's big CDs. You guys remember CDs? And I had a little bug sitting here, and then I have another little bug sitting there, and I start the record going. Which bug's linear speed will be faster?
The one closer to the center.
No. And think about it. Which bug? So as the record player turns, don't they both stay on this line? If they're, let me just say they're stuck there, poor little bugs. They went to sleep and got, thing melted. It's really gross. And then I start playing my record. I don't know. This is a weird day. Just leave me alone. As it turns, don't they stay? So a little bit, like just a little, just a second later, maybe it's here and here. Who has gone farther? Who has traveled farther?
The one on the outside.
The one on the outside. Yes, I like it. So that's the one that's experiencing a greater linear speed. But the angular speed, so what the hell would angular speed mean? Well, angular speed must mean the amount of radians you go through per time unit, right? That must be what angular speed is. How many angle units you go through per time units? That would be angular velocity if you want to really get fancy. Would be the number of radians, or even just the angle you pass through over a certain amount of time. So if I put my given units in, the most, I don't know if you picked up on this, but the most commonly used symbol for angles is theta. That is the most commonly used symbol for angles, is theta. That's like X for algebra. So this is going to be theta. This is going to be unbelievably T. And then we got to give this guy his own unit. So we're going to call this little dude omega, which is basically a little more curvy W. So if you already make curvy W's, okay, I'll figure it out. W is not used too often for much anything else anyway, so it'll probably be fine. This is the official formula for angular velocity. Again, notice, what's this top got to be in? What units?
Radians.
Radians. I like it. So if the record, I don't know if this is going to make any sense. If in 1.2 seconds, let's say the record turns through, you could do it, Jeff. Let's say 1.29 radians. Just to show you, you can have decimal radians, like somebody's multiplied the pi in. Then what is the angular speed of that record player? So in 1.2 seconds, it goes 1.29 radians. So I just got to plug and check. Right? So my angular speed will be 1.29 rads per 1.2 seconds.
1.075.
Sure. Rads per second. So both of these bugs are experiencing the exact same angular velocity. Neither bug has gone through more or less angle than the other one. Do you guys get that? Okay, I like it. Now, there must be a connection between angular velocity and linear velocity. There's got to be a way to convert from one to the other. And what is conspicuously, let me see if it's conspicuous or not. What's missing from this equation that's in all the other equations we've done so far?
The radius.
The radius. So notice these are not really angular ideas. They aren't. This is the length and this is an area. So they do involve R. They're more linear ideas, right? In fact, that's all S is. Notice what this, I want you to get this. I can look at this equation as a transformation from an angle and to a linear distance. That's what this does. Do you have to look at it that way? No, you don't, but it is kind of nifty, especially when we get to the equation we're going to get in a minute. All right. So let me use this bad boy to help me figure out the connection between this equation and linear velocity. So let me ask you this. What would linear velocity be? The linear velocities for both of these bugs would be different, correct? And let me see, can somebody tell me exactly why? Based on what I just said about what's missing up there?
It would include the radius.
Yeah, because this bug's radius, this bug's effective little circle it's on, has a much smaller radius than this bug's, right? I like it. All right, so let's do this. Let me take away some of the stuff. Let me throw this up there to be one of our toolbox equations. And now let's remember another equation. What would the equation be for velocity if I know this bug went S over t seconds, right? So I basically just gave it away. How do I figure out velocity? It would be distance traveled divided by time. All right, let me stop for a minute. That hasn't changed. So even if you're running around a circular track, how do you figure out your velocity? Well, you figure out the distance you traveled. It's going to be an arc length. I don't give a shit. The distance you traveled divided by how long it took you. Right? That's velocity. How's everybody doing up there? You guys all right? I love this. So few people turn their camera on nowadays. It's okay though. I'll be all right. Now, what's the connection between these two? What connects those two? What's the only thing that they have in common?
Time.
Time. So that's something to notice. So there's two ways to go about, what do I want to say? There's two ways to go about using these with each other. And I've got this guy. So let me write down everything we want to use. We've got this guy. We've got this guy. And we've got this guy. The very first thing you should notice. Well, let me see. What's the very first thing you guys notice?
You can have r theta over time, and then both w and v have the theta.
Yeah, you could put like r theta in here, right? But then you could solve. So there's a multiple different ways to go. So let me just help. I just want you guys to realize what we're trying to do is to get v in terms of omega. I want to see the connection between these two, right? So one thing I could do is I could actually solve this guy for theta. All right, let's do that. This is not the only way to do this. As Jason already pointed out, there's other connections. So then what does this become? If I do this, what does that equation become?
X equals R times WT.
Yes, S is R omega. I'm sorry, I haven't said this yet, did I? This is omega. Or did I say that? I can't remember now. So R omega T. So omega is a little bit more curvy W, but I'm not really trying, am I? Oh. And then the what can I do now? Now I can replace S with S. And then finally I can kill the T's. Right, so that's going to happen eventually anyway. So now I get linear velocity is R times angular velocity. Now why does that make a shit ton of sense? Linear distance is R times angular distance. Linear velocity is R times angular velocity. That kicks so much ass. It kicks ass. Might be just me. And let me try to, let me see. Let me think. Okay. This is kind of important. And this is another thing that I wasn't taught early on that I think will help students. So every time I teach this, I say this. Remember the basic definition of radian, right? Was S divided by theta? No, S divided by R. Thinking ahead. Right? And what units would these both have? I mean, R is a radius, S is a length along the circle. So wouldn't they have the same units? Maybe centimeter over centimeter or something. Go with me now. Okay, okay. So what happens to all the units when I put them in? What happens to units? So if I had a circle and the radius was 7 inches, I don't know what's up with 7 today, and this arc length was 8 inches. So when I do 8 divided by 7 inches, what happens to the units?
They cancel.
Cancel. So officially, I really want this to make sense. In a very real capacity, this is a unitless thing. But at the same time, it makes sense that it is a number of radians, but it's not really, it doesn't have units. It's a number of radians. So if I had a radian, if I had an angle of 2 radians, that means that it's 2 radii to get there. There are no actual units. It's not in miles. It's not in feet. It's not in anything. It's just a number of radians. So now watch this. All right. So everybody got this. I'm pretty sure everybody's got this business here. And again, everything I'm saying outside of deriving these are just extra shit that makes it easier to understand stuff coming. What units is this in? So let me put it's, well, here's its form. What units is omega in? What units is omega in?
Radians.
I know you're, yes, radians per second, for example. Let's see, yeah, just give an example. You're right, because it could be minutes out. Radians per second. And a velocity is supposed to be in like feet per second or something, right? So if I take a radius, which could be feet, times something that's radians per second, here's what really is useful to understand. This isn't really there. All right, this might be freaking you shit out, but that's what the whole purpose of me saying there really is no units on an angle that's in radians. Because that doesn't mean centimeter, it just means number of radii. That's all it means. It's not really a unit. So then what happens here is it becomes feet per second. So this is sort of like a placeholder in a way. So it doesn't become linear until I multiply it by something linear. So that's why this works this way. Theta times r becomes a linear distance. Omega times r becomes a linear velocity.
So if it's asking us to find theta, you don't want us to put radians after the answer? Or
You actually don't. You actually don't have to. Very good point. So if they said, so coming up, we are going to learn, and let me see, I'm sure that some of you guys have seen this before, but we're going to learn this function. So it kind of is a lot like log, except not at all. It's only like log because it looks like a word, right? So this is not the original sin. This is obviously way after that. And you know, I'm not really religious, but whatever the hell. What was I trying to say? What were you just asking me? Why did I go off on this joke? Why did I do that to myself? You were just asking me what again?
If it was asking you for theta, if you would have to put radians behind.
Okay. So if I see this problem, I know that's radians because there isn't a degree on it. So very good question. You do not have to put the rad on it. I just do, especially now, but you might want to kind of get used to it too, just to be safe, just to make sure that I know and you know what the hell it is, right? But yes, officially, if I see this, I have to assume this is 20 radians. In fact, I know it is, because if they meant degrees, they would have put a little degree on it. All right, I like it. All right, let me see. What was the last thing? Oh, let's see, how much time do we have? Maybe we can do one example. Let me pull an example out of the book, I think, just to be on the safe side. If I make one up, it's probably gonna get freakadelic. Do strangers in the mind, stranger close. All right, come on. I don't want that section, do I? Yes, I do. Yeah, I want the one about, maybe I will make one up if I can't see it any good in here. No. Here, yeah. Okay, sure, okay. Yeah, so let's see, they have a, this is a try it number 10 if you want to look in your section 7.1, but it's an old vinyl record is playing on a turntable. We got some records going. rate of 45 rotations per minute. And they want to find the angular speed, omega. What's the angular speed in radians per second? Yeah. So when you see this word, what does that mean? What's rotations? What does one rotation equal?
2 pi.
2 pi, kick ass. Not a big deal, right? One rotation is 2 pi. Now, in another problem, you might actually have to make it into, you might have to take into consideration the circumference of the thing. So 45 rotations would be 45 times the circumference, right? But this is all about angles. So 45 rotations, I can just change this directly into what they want. So 45 rotations per minute equals 45 times 2 pi radians per 60 seconds. Is that all right? So that was less of a problem involving formula as it is involving just straight up conversion. So let me see if we got a part B to that bad boy. So now you just figure out what that is. 9, 6, so 3/2. So what is that? 1.5 pi per second. Is that what it is? Radians? I think it is. 3 pi 2 rads per second. Is that what it is? Yeah, so let's try one more and then I'll call it a day. So pretty cool with that one. That one was pretty straightforward. That one was kind of nice because they gave us the velocity in rotations per minute. So it was just a direct conversion to radians per second. All right, so one last one, and then I'll call it a day for all of us. So now I've got a bicycle wheel, and it's 20 inches in diameter. Tachometer determines the wheels are rotating at, so it's rotating at 180 RPM. Find the speed the bicycle is traveling down the road. Okay, I like this problem. I kind of don't like it because they don't really say what units, but that kind of leaves it open to, we can leave it however we want. So what do you notice first here? What kind of jumps out at you? So I want the speed of the bike. So that's very often that's where I start, to be honest. And then I see, well, what is there a formula that will get me here? And of course, what is that formula?
The linear velocity formula.
Yeah, linear velocity. So now I know what I need to figure out. And of course, in this, what do I know? I know R is what?
14.
14 inches. And what else do I need? I need omega. What do I know about omega at the moment?
Omega equals 180 RPM.
Yeah, what's RPM?
Rotations per minute.
Yeah, rotations is actually revolutions, but it's the same thing. Revolutions per minute. So I need to convert this into radians per minute. Right, because I know that my angle has got to be in radians. The seconds was just an example. It could be any time unit that I want. Is everybody sort of with me here? Are you guys doing okay out there? I have no idea. Some of you guys might have used this much more than others already. These angular analogies to linear stuff. I don't know. So what would I do here? 180 times
2 pi.
2 pi per minute. So now to find the velocity, I just have to do R times theta. I'm sorry, omega. And the rads are going to kind of get out of the way. The inches is kind of take over. The rads are sort of a placeholder. And I really hope you guys kind of get that. That was something that was never really explained to me fully. And I just accepted that they sort of went away, but that they're not even really there in the first place. It's like number of erasers across the board. It's not really a unit. And then whatever the hell this is, I don't know. You have to multiply all that shit out. No idea. And it'll be in inches per minute, which is not the most useful measure, but they didn't really tell me to get it into any specific units. We probably want to go into miles per hour, right? But I think whatever the hell you get there, that's fine.
When we give our final answer, do you normally want us to leave it in pi form, or do you want us to multiply it all out?
So that's a very good question. When it's a physical problem like this, you almost always want to go ahead and multiply the pi through, and you do that at the very end, right? So that there's not a lot of rounding before you get to the end. Because, you know, I'm not going to say, man, I was riding my bike about 6 pi mile an hour. It's like, who the hell are you? What? So it's a good question. So normally if it's a physical problem like this, we do want to go ahead and multiply by pi, just so it matches what we say in real life.
Okay, got it. Thank you.
Cool. Well, now sometimes the problems might say one or the other way, but yeah. One thing we do almost always write with pi is radian measure, but even that's not a hard fast thing at all. So you guys doing all right out there? Any questions from all that? We did what seems like a lot, but to be honest, we just finished 7-1. 7-1 has got quite a few things in it.
So the quiz on Thursday.
Sorry. Say again, sorry.
The quiz on Thursday, it's just the rest of 6, correct?
Yeah, it's did you guys notice? I forgot to make sure you guys noticed this, but I put up part 2 of 3 of the homework sheet up on Canvas. So now it's got the corrected dates for the quizzes and what they'll be covering. So the next quiz is October 8th, 6-3 through 6-6. 6-7 is not on there. We talked about that earlier. It's going to be long enough with 6-3 through 6-6, so that's plenty. So check that out. That's part 2, and then below that is part 1 if you need to see that again. Part 1 gets us through November, so I'll be working on finishing that out between now and then. All right. I'll officially call it. Let me know if you have any questions and you want to hang out afterwards. Otherwise, you are free to go anywhere else you want within reason.
Thank you.
You are welcome.
Thank you.
You're welcome. Later.
I have a question about the homework sheet that you just posted.
Yes.
So the old one has a 6.8 on it. The new one does not have 6.8 on
Right.
it. So we're
Right.
just not supposed to do 6.8.
I mentioned that last time. 6.8 was a optional section in the first place. So I'm always optimistic about my chances of getting to these things. So that was one of the sections that I was free to get rid of if I felt like it. Now, to be honest, I can make it official and say if you want to do that as extra credit, that's fine. So let me, if somebody will email me and remind me, make that official. If you want to do that for extra credit, I don't mind that at all. Yeah. But officially, it's not a part of the curriculum anymore, so we're good.
Okay, I'd be up to do that. Yeah.
Great. All right, just remind me. Shoot me an email. I can make a little place for it in the modules, and then I can email the class and tell everybody.
All right, will do.
Thank you.
Okay, see you.
How's everybody else? Oh, everybody's leaving. Okay. Any questions, guys? I'm gonna head out. All right. I'll see you all later.